just to make sure that you all know that you are in the right place. My name is Anne van der Velde, and this is first class of hematology. So if you're here for anything else, this is the time to find another room. And can I ask you before starting, maybe please to shut down your mobile phone, because it can be sometimes embarrassing during a lecture. Sorry for asking that. So today we will talk about haematopoiesis. And haematopoiesis comes from the ancient Greek, means to make blood. So we will discuss in much more details how all our different blood cells are formed. So you probably remember last week's lecture where we talked about the hematological organs. And maybe just to start with, can somebody of you tell me what these hematological organs are? Yes, that's one of them. Does somebody has another answer? An extra hematological organ? Yes, that's also very true. And maybe the last? The liver, yes. But you forgot two other organs, and that means the lymphatic tissue and the thymus. Now today we will focus on the bone marrow itself. And why? That's because of most of the haematopoiesis takes part in the red marrow. And the red marrow we can find in mostly in the flat bones when we are an adult person. Now, can you name some of these flat bones? Excuse me? Yes, that's correct. Other flat bones? Maybe this figure can help you. Very true, and the pelvis, we mostly use it in daily practice for bone marrow examination. And maybe another one, because there are many flat bones in our body. Yes, perfect. So I'll go to them together. We have the cranium. Nobody mentioned the cranium. We have the sternum. We have the vertebrae on the back. We have many ribs, also flat bones. The scapulae, the pelvis. And then the red marrow we also find not only in the flat bones, but also, as you see in this figure, in the long bones, like the femur and the humerus. Now let us come back to haematopoiesis, and where does it all start? It starts with the hematopoietic stem cell, and the hematopoietic stem cell is a very special cell. She resides deep in the bone marrow, and we also call her often the mother cell. Now she has two features, very distinct. She is pluripotent, and she is immortal. Now that means that she can constantly renew herself, she never dies, and she can turn herself into the many different mature blood cells. Now the mature blood cells, we know them, we see them in daily practice very often, and you see them here on this horizontal line. And let us start with naming them by names, starting from the left, that are the platelets. The platelets, we also call them the thrombocytes. Now the thrombocytes, they are part of our hemostatic system, and that's very necessary because it will heal after an injury so that our blood volume stays constantly the same. Now next to the platelets, we have the red blood cells. The red blood cells, we call them the erythrocytes. The erythrocytes, we need them because they carry oxygen and carbon dioxide through our body, so that a lot of our muscle tissues is fed. Then we see a lot of these cells. Now these cells are all part of the white blood cells, the leukocytes we call them, and this is the myeloid part of the white blood cells. Myeloid part means that we have these three different kinds of cells. The granulocytes. The granulocytes, they contain granules in their cytoplasm, and depending on the color, they have a different name. So from left to right, we have the basophils, the neutrophils, and the eosinophils. And then part of these granulocytes, we have the macrophages. Now, the other part of the white blood cells is here, and it's mean the lymphocytic part. So you have the B and the T lymphocytes. And hematopoiesis is the way this hematopoietic stem cell matures to all these different blood cells. So you see this here in a whole figure. And the hematopoietic stem cell goes to the mature cells by two possibilities. Or she goes by the myeloid lineage, or she goes by the lymphoid lineage. And if she goes by the myeloid lineage, she will form the platelets, the red blood cells, and the myeloid cells of the white blood cells. But if she goes by the lymphoid lineage, she will form the lymphocytes. And although on this graph it seems like the myeloid differentiation is much more complicated, today we know that this pathway is much more convoluted because to go from this step to this final step, all these precursor cells needs to go through the lymph nodes and the thymus. And scientists today are... Does somebody has his phone still on? Oh, sorry, I really have to answer this one. Sorry. But Ali, I'm in the lecture, I'm giving the lecture. Get Martin to clerk him in. What? What? How high is his white blood cell count? 230,000? Okay, I'm coming. I'm on my way. I'm so sorry. I have an emergency on the wards. I'll be coming back to end this lecture, I hope within 15 or 20 minutes, as soon as possible. It's called Philadelphia chromosome positive acute lymphoblastic leukemia. It means you'll be with us for a while longer. You're responding positively to the induction chemotherapy, we're seeing a drop in the malignant white blood cell count. If this continues, you'll get into remission within 6 weeks. But the problem with this disease is that remission doesn't tend to last very long. So we need to give you a very strong consolidation therapy. Myeloablative chemotherapy to wipe out the remaining diseased cells from the bone marrow, and radiotherapy to ensure that there are no dormant leukemic cells in the brain. It's an aggressive disease, and we need to treat it very robustly to prevent relapse. Do you have a brother or sister? One of the post-remission treatment options is a stem cell transplant. A transplant will give you the best chance of long-term remission, but its conditioning regimen is very strong. The chemo and radiotherapy will damage all your healthy cells and leave you immunocompromised. So we can only proceed with it if we have a donation of healthy stem cells to reboot your own hematopoietic system. There are some risks associated with a transplant, but it's our preferred course of action. Negative complications of a stem cell transplantation include infection, graft versus host disease, and graft failure. Each of these is potentially fatal. However, for diseases with poor prognostic outcomes, such as leukemia, a stem cell transplant represents the best chance for long-term survival and cure. Thus, the risk of a stem cell transplantation are outweighed by those of the disease itself. A transplant is therefore the optimal post-remission therapy for patients who are strong enough to withstand the therapy and who have a matched donor. A matched donor is someone who is genetically compatible to the recipient, and a good level of histocompatibility reduces the risk of graft versus host disease when the donated stem cells recognize the patient as foreign and can attack him. In order to ascertain whether someone is a compatible donor, we look at human leukocyte antigens, called HLA. Antigens are proteins that appear on the cell surfaces. This specific set of HLA antigens, located on chromosome 6, determines whether or not two people's immunological responses are compatible. There are two classes of HLA antigens. Class 1 are HLA-A, B, and C. Class 2 are HLA-DR, DQ, and DP. If two people match at each of these 6 loci, we call it a 12 out of 12 match. However, each HLA antigen expresses more information through its various alleles. This is called allelic polymorphism. There are currently being identified 1,884 alleles for locus A, 2,490 for locus B, 1,384 for locus C, 1,194 for locus DR, and 165 for locus DQ. Thus the chance of a possible matching is 10 to the power of 23. This is a serious obstacle to transplant, and the reason why we always start with the patient's siblings when looking for a donor. There is a 1 in 4 chance of a sibling being a match. For patients with no matched siblings, we look through the bone marrow registries, which keep records of HLA data of potential donors. Worldwide, over 20 million people have joined a stem cell donor registry. The chance of finding a match with a voluntary donor is 50%. The donor's blood is being drawn out of his body from one arm and into this machine. Down here is the centrifuge. There's a belt and a spinning action. So the blood that's coming into the machine is spun in order to separate out the stem cells. These stem cells are collected in a closed system bag. In this tubing here is a blood warmer, so the donor doesn't get chilled when the blood goes back into his other arm. These other bags, one is saline, one is an anticoagulant, and one is calcium. At any given time, about 280 milliliters of his blood are in the machine, coming out of the one arm, through the machine, and back into the other arm.